Hi, I'm Ben from the Things Industries, and today I'm going to show you how to add your devices to the LoRaWAN device repository. Adding your devices to the device repository makes it really easy for users to add your device in the Things stack, and we'll also use it to add devices to the Wall of Fame during the Things conference. So adding your devices is a win-win-win. All you'll need today is your computer, a GitHub account, and probably a spec sheet of the device that you want to add so you can look up information to add it in the device repo. Let's get started. So step one is to clone the device repository so that you can add your devices to it. Head over to the GitHub repository and hit this fork button in order to make your own copy. Once you've forked the repository, you can either use this download zip button in order to download the files, or you can use the command line to clone the Git repository. I prefer the command line. So we'll do a git clone, and then I'll paste the address of that Git repo, and that will automatically clone it into a folder with the same name as the repo. Then I can enter into that folder. And now I'm going to open Visual Studio Code to edit the files. So I'll go ahead and open that project folder. And here I can see all the files. Visual Studio Code has an extension which allows you to automatically validate the YAML documents that we'll be editing. So if you go into the repository, we have a link that you can use to easily install that plugin. So that's just right here. And then go ahead and click install, and that will open Visual Studio and install the plugin. To make the plugin work, you may also need a .vs Code settings.json file, which we have instructions for in the repository. And I can see that file here in VS Code settings.json, and all it does is specify the schema file which VS Code will use to validate my YAML. In the README in GitHub, we have instructions for adding your devices, and so I'll go through those now. The first thing to do is make sure that your company is listed in the vendor index. So in vendor/index.yaml, we have a list of all of the companies with a vendor ID from the LoRaWAN Alliance. If your company doesn't have a vendor ID, you can still go ahead and just add the company at the bottom. So today, I'll create an imaginary company called TTC Vendor. The nice thing about Git is that you can always see what you've done by typing git status. So here I can see now that I've made changes to this vendor/index.yaml file where I've added my company name. The next thing to do is to create a folder in the vendor folder that represents that company ID. The easiest way to do that is just to copy the example folder. So I'll copy the example folder. And now I've got a copy, which I will rename to match my company ID. Great. Now inside that TTC vendor folder, we have an index.yaml file. And there, all of the devices that we offer are listed. The example contained one device called WinSensor, and so I'll change that to my device. I'll just go through and modify the examples, and I'll leave the comments as they are because they're helpful when you're filling out your device information. So my company makes one product called TTC device. If your company makes more products, you can also list them here. For example, but I'm just going to make one product. End device IDs must also be lowercase and up to 36 characters with only dashes. You can specify the actual name of your device inside the YAML file, which corresponds to that device. This end device should have a matching YAML file in the same folder, which describes that device. So let's take a look at our corresponding file, which was winsensor.yaml, and we'll rename to ttc device.yaml. So now our end device ID is matched by our TTC device YAML file. And here I can go and update the name and give it a description. And you can see here, we have fields for the hardware versions, firmware versions, sensors, dimensions, weight, battery, operating conditions, and plenty more. If you use the YAML extension, you can also press Control Space to see additional available fields. If your device has hardware revisions, go ahead and enter them here. And firmware can also optionally correspond to a particular hardware version, if a firmware version is, for example, only compatible with a particular hardware version. In the Profile section, we allow you to specify a LoRaWAN device profile for each region. The supported regions are listed in the comments. The example uses the same profile for EU 868 and US 915. And so we're going to change that and create separate profiles. This profile ID corresponds to a YAML file which specifies that profile. So here I can see that WinSensor profile corresponds to this WinSensor profile.yaml file. I want to create separate profiles for 868 and 915. So I'll go ahead and duplicate this. And then I'll create two different profiles. And now I have a profile for 868 and 915. And I'll change the max EIRP, which is different for the 915. These profiles are really useful if you have multiple devices which all use the same LoRaWAN device profile, because you can just define that profile once and then specify that file from each of the devices. Now in our device profiles, I'll go and I'll update this profile ID to match those regional specific profiles which I created. So that's TTC device 868. And in 915, the codec is used to specify uplink and downlink payload formatters, and that's a little bit complicated, so I'll do that last. Let's quickly take a look through the rest of the file. So here you can add additional firmware versions. In this case, I've only got one firmware version, so I will remove this. You can specify sensors, and in this case, we're going to create an imaginary device that has a temperature sensor and a light sensor. You can specify dimensions, you can specify weight, battery, operating conditions, if your device has an IP rating, how keys are provisioned, if you have integrated key security, you can specify product and data sheets, you can add photos, you can link to video, and then you can also specify regulatory compliances. All of these are optional, but obviously the more information you add, the more helpful it is. Only one firmware version is mandatory. Let's go ahead and update our photo. So I'll add a picture. And now I've added my TTC device.jpg, which is a photo of my device. So I can update these photos elements to reference that file. And I've just got one photo, so I'll get rid of the other. Lastly, I'll explain codecs. Within the regional profiles, codecs specify a file which contains uplink and downlink payload formatters. This ID matches a YAML codec file with that specification. In our codec file, we can specify an uplink decoder, a downlink encoder, and a downlink decoder. Let's assume our device has a light sensor and a temperature sensor. I can create examples to test these encoders and decoders. So for example, let's say our device sends an uplink with F-port 1 and the bytes which correspond exactly to the number of degrees that it measures. It's not a very precise temperature sensor. In that case, I'll expect an uplink with a value of 10. So I specify that in the example. So if the input is 10, that should produce an output equal to temperature 10. And let's say we have a binary light sensor, which just produces a 1 when there's light. So if that comes in on F-port 2, then we would expect to see a 1 in the uplink. And that corresponds to a decoded uplink of light 1. These are really trivial examples, but hopefully when we look at the actual decoder, it'll be clear how they work. For the uplink decoders, the input is the payload, and the output is the decoded message. It's also possible to specify errors. Let's assume that our light sensor also has an RGB LED on it, and so the wind sensor downlink encoder and downlink decoder examples will already work. If I send a downlink with an input data LED with a value of green, I expect that to produce a downlink with an output message of 1 on F-port 2. And if I send a downlink with input data LED and a value of blue, it should throw an invalid LED color error. The downlink decoder does the opposite. It should be symmetric with the downlink encoder. So whatever the encoder produces, the decoder should produce the reverse of. In this case, a downlink with a value of 1 should correspond to data LED green. I'll also want to make sure that I specify the file name which contains the uplink and downlink decoders. Let's go take a look at those. This JavaScript file contains functions for decoding uplinks, encoding downlinks, and decoding downlinks. Uplink decoders receive an input object, and that input object contains the F-port and the bytes. Our imaginary device sends the temperature on F-port 1, so we'll go ahead and write an uplink decoder for that. If our F-port is 1, we want to produce an object with a temperature value equal to the bytes, since our very inaccurate temperature sensor sends 1 byte. If we get an fport2 uplink, that corresponds to our light sensor. A value of 1 means that the light's on, and a value of 0 means that the light's off. So we just pass that directly into the light data field. So now we have an uplink decoder. And for example, if an uplink message comes in with fport1 and a value of 1, that means that the sensor registered a temperature of 1 degree. If a message comes in with fport2 and a value of 1, that means that the light sensor was triggered. A 0 means no light. We're going to use the example downlink encoder and decoder, which take one of the colors we've specified here, red or green, and turn them into a message with fport2 and bytes which correspond to the position in this array of that color. So for example, a message with input.data.led equals green will produce bytes 1. The downlink decoder simply does the opposite. It takes the binary data and produces an object with a human readable color. I'll rename this file to match what we specified in the codec. And I'll also rename the codec. Forgot to do that. So now we have our codec, which specifies our actual encoders and decoders. In our device YAML, we want to specify that codec. We can get rid of these old images. Now we should have enough data to add this TTC device to the device repo. Let's go validate that. To set up the repo, type make deps. Let's validate our data. Type make validate, and that will run validation. So here I got an error. It looks like I have an error because my uplink decoder doesn't match my example data. Let's go take a look. It looks like I just forgot to save. Let's try again. And validation passes. Like you saw, if you make an error somewhere, for example, if we specify a sensor that doesn't exist, then make validate will produce errors. So let's fix those. Validate, and validation passes. Once you've validated your data, do an additional make validate format. Now we're ready to submit our device to the device repo. We can use git status to see what we've changed. And then we can go ahead and add all of those changes to a commit, which will push to the repository. Git add dot adds all of the changes that you've made. Git commit -m allows you to specify a message which explains what you did. So here I'm creating a commit with a message add TTC device. Finally, I'll push that to my fork using git push. In GitHub, in my fork, I can see that I'm one commit ahead of the master. In order to submit my changes for review, I'll create a pull request. Just click pull request. GitHub will show you a comparison of the changes that you've made. I can see exactly what I've added. And then I hit create pull request, and I can provide a description of exactly what I've changed. In this case, I've just added my TTC device. When you're ready, hit the create pull request to actually submit that pull request. We'll then see your changes in our repo, and we can review and actually merge your changes in. And that's it. That's how you add a device in the device repo. I hope that was helpful. Thanks for watching, and thanks for using the ThinkStack.